Good day, I'm Norman Walberger. Today we're going to have a look at our new framework for maxels, where we extend our labeling set from natural numbers to integers. So this extends our view so that we're essentially covering the entire plane now with possible pixels. So it's a much broader framework, and we want to review some of the hopefully familiar aspects of the previous maxel theory to this new setting. So it'll be a chance of, first of all, reviewing some important things and also getting you used to thinking more two-dimensionally about linear algebra. So the basic object are these things called maxels from integers, where we're considering multi-sets of pixels, where the pixels themselves can have entries which are integers, including both negative and natural numbers. So here, for example, is a maxel. It's an M set of pixels, and the various pixels can be represented by their positions on this screen, which we might call the integer screen. And it's typically in green here with these two prominent vertical and horizontal bars that align things and tell you sort of where the indices start. So this is the central element whose indices are 0, 0, and then we go down here, the first entry increases. So this is 0, 0, 1, 0, 2, 0, and so on. And when we go to the right, we go 0, 0, 0, 1, 0, 2, 0, 3, and so on. And that, of course, then extends to the negative values as well. So, for example, this 3 here is referring to the fact that we have 3 pixels of this kind of type -2, -1. So that would be -2, -1. And the other important ingredient is our multiplication of pixels, which is the fundamental building block for the algebra of maxels. This is the crucial multiplication, that KL times Mn is equal to Kn, provided that L equals M, and is otherwise blank or empty. Okay, and this multiplication now is a multiplication of pixels from integers. So now the entries here can be integers, not just natural numbers. All right, so let me remind you of some notation, some basic notation that helps us understand maxels. The idea of a one maxel, which is a simple kind of maxel that only has one element in it, a single pixel, namely ij. Now, of course, the I and j indices can be any integers. Special kind, the diagonal one maxels, they're of the form EII. So the two elements are the same. These are occurring on the diagonal. And they have the idempotent property that EII squared equals EII. And if you multiply one of these diagonal ones with another one, you either get the one that you started with if they're both the same. That's basically this rule here. And if they're not the same, if these numbers are not the same, you get the zero maxel. So this 0 here represents the zero maxel, or the empty maxel, just the empty set. And here's our picture of our screen with our two canonical vertical and horizontal lines. There's the 0, 0 spot. So this now is the place or the home for E0, 0. Here's E1, 1, E2, 2, E-1, -1, E-2, -2, etc. So actually, if we actually drew a representation for, say, E-1, -1, we would end up with a single 1 there and zeros everywhere else. So these are kind of units in the world of maxels. And prominently, we can go either in this direction, so we can carry on in this direction, or we can carry on in this direction here as well. So there's a two-sided aspect to things. Now, suppose that J is a set from integers. It's a set of integers. Then E sub j is the sum of little j belonging to capital J of these EJJs. And I need to remind you that when I say set, I always mean something that you can actually write down. So it's an explicit set in our standard notation, so it's by definition finite. Okay, we don't even consider infinite things because you can't write them down. Okay, so this kind of object we'll call an identity maxel, or maybe a partial identity maxel. For example, if J is the set minus 2, 0, 1, then it can be represented, the E sub J, here. So here's our basic two lines. It's a bit of a crowded diagram, but you see a 1 there. That 1 represents that 0 there. The minus 2, there, that 1 there, and this 1 represents there. So this thing here is E11, this is E00, and this is E minus 2 minus 2. So in terms of pixels, here is the M set E sub J. So let's just talk a little bit about rows and columns. So we have this J. We can also talk about the rows of J and the columns of J, and that will be important for us. So the rows of J are just the rows that go through the various entries of J, while the columns are these ones here, again, they're going through the various diagonal entries that is represented by J. So here we have the rows of this particular J, and here are the columns of this particular J, 3 of each kind. Now, if M is any maxel, then the product E sub J M is the restriction of M to the rows of J. Okay, the effect of multiplying by E sub J, this is just the same kind of story that happens in the situation that we started talking about, where we were just restricting to indices 1, 2, 3, and so on. The algebra is completely the same. That E sub Jm is the restriction of M to the rows of the J, while the other way around, M times E sub J is the restriction to the columns of J, namely the restriction here. In other words, basically forget about all the entries of M which are outside the columns, or in this case, outside the rows. And then if we combine those two ideas, we have a maxel M, and we multiply on the left by E sub J, and on the right also by E sub J, then we get the cumulative effect of restricting to the rows of J and to the columns of J. So for example, if J is the same as before, minus 2, 0, 1, then E sub J looks like this, and here's E sub J as well. And suppose we take some arbitrary maxel M. We multiply by E sub J on the left and E sub J on the right. What do we get? Well, it's an excellent exercise to convince yourself that this is what you get, that we end up just looking at the rows and the columns associated to the J. So the rows of J would be the minus 2 row, the 0 row, and the 1 row. And the columns of J would be the minus 2 column, the 0 column, and the 1 column. And if we ignore everything which is not in both the rows and columns that I've just mentioned, then we get this thing here. So this is the restriction of this to the row minus 2, 0, and 1, and to the column minus 2, that one there, 0, that one there, and 1, that one there. So everything below, outside, gets killed, and everything that's in, say, one row but not a column ends up being killed. So the only entries that are left are the ones in the rows and columns of J. So this is very much paralleling what we've done in previous videos when we talked about maxel algebra. So you might want to go back to some of those to remind you. So if we have a set J, a set of integers, then we can consider J cross J. And by that we mean the set of lists of the form J1, J2, where J1 and J2 belong to J. So this is a set of pixels from integers, because this is just a pixel from integers. And a set of pixels from integers we'll call a frame. So then max J cross J is the type of a maxel M whose support is in J cross J. So with our example of J equals minus 2, 0, 1, here are our standard lines. So there's the 0, 0 position. Then the J cross J frame looks like what? Well, first of all, here's E minus 2, E 0, 0, and E 1, 1. So here are sort of the basic entries, the diagonal entries that define E sub J. And then the things that or the positions that correspond to columns and rows are just these ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the pixels whose rows are either 1, 0, or -2, and whose columns are either 1, 0, or -2. And there's 9 of them. So when we talk about max j cross j, we're talking about all the maxels whose support is this, or is contained in this particular frame. The frame consisting of these 9 positions in our integer screen. So this is going to be a maxel subalgebra of max int. In other words, if you take the product or the sum of any two such things, you're going to stay inside this closed algebra. So this is a very nice, flexible way of finding essentially what we might call matrix algebras, okay, traditionally, but we can find them now anywhere or everywhere on our screen in this kind of symmetrical way. You pick a subset J of integers, and then that's basically picking a bunch of diagonal elements along the diagonal, and then associated to that you have this something like a square thing, but it's not graphically a square, but it's arithmetically a square of positions that support this maxel subalgebra. Okay, so this is by way of a review, but also an extension of the ideas that we had before in the natural number case. We're now extending this to cover the entire plane. That's the crucial difference. We're now allowing arbitrary integers to be indices for our pixels. Now we are going to be seeing that this maxel algebra extended to integers has a lot of beautiful properties that will be very useful for us when we want to talk about extension fields or more general sort of field theory. But we'll also see that it has a lot of connections with calculus, and having this two-sided aspect of things will play a very big role when we connect things with calculus kind of ideas. And a very useful tool in this understanding is the idea of shifting along the diagonal. So it turns out that the entire maxel framework that we've been talking about is kind of invariant under shifting diagonally along the diagonal line. And we can make that more precise by introducing a formal shift operation. So for k an integer, let's define s sub k. This is going to be a shift on pixels from integers, defined the following way. So here mn, that's a pixel from integers, and s sub k is our shift, and by definition this is going to be m plus k, n plus k. So all what we're doing is we're adding k to both the values at the same time. That's effectively shifting it diagonally. In this direction if k is positive, and in this direction if k is negative. Okay, so now I'm going to leave you a couple of exercises. So the first one is to show that this respects multiplication. This is the kind of crucial one. That if you have two pixels, P and Q, and you're interested in multiplying them, then the shift of their product is the same as the product of their shifts. So if you shift P and you shift Q and then you multiply, that's the same as first multiplying P and Q and then shifting. And also show that there's a kind of composite property, which is almost obvious, that if you shift by K and then you shift by L, it's the same as shifting by L plus K. So the shifts themselves have a kind of pleasant algebraic aspect. So generally speaking, once we've defined something for pixels, we want to extend that to maxels, which are just m sets of pixels. So we know how to shift pixels, so it follows that we should be able to shift maxels just by doing the m set version of the shifting, namely shift all the pixels in a given maxel. So we'll do that. So we'll define the shift s sub k is still an integer, now from pixels to maxels, and it's just the m set extension. Let me illustrate it by an example. So here is a maxel. It has a few pixels, 4 of them, and let's say that k equals 2. Okay, so then s sub k of m, we're going to apply s sub k to each one of these pixels. So it's a new multiset with sk of this, then sk of this, sk of this, and sk of this. And each one of these individually, we're just shifting by 2. So if we shift this by 2, we get 0, 5, also 0, 5. Here we get 3, 2, and here I guess we get minus 1, 1. Diagrammatically, this maxel here is, let's see, there's a minus 2, 3, minus 2, 3, so there's 2 of them. There's a 1, 0, that's that one there, and there's a minus 3, minus 1. 1, 2, minus 3, minus 1. So this is the representation of this maxel. And when we shift it by 2, it means we're shifting in this direction here, diagonally, so everything goes down in that direction. 2 down this way, 2 across this way. So the 1 that's appearing here goes there. The 2 that was here goes there. The 1 that was here goes there. So the whole thing has just moved down diagonally by 2. And now let's identify some important features of this shifting of maxels. We could say shift invariance for maxels. And let's summarize things in a theorem. So if k is an integer, and m and n are maxels from integers, then the shift skm plus the shift skn equals the shift sk of m plus n. So it respects addition. If you add 2 maxels and then shift, it's the same as first shifting and then adding. That's almost obvious. This is a little bit more subtle, that skm times skn is sk of mn. If you multiply m and n and shift, it's the same thing as first shifting m and shifting n and multiplying them. So to summarize, this shifting does not really affect the algebra of maxels. This is an aspect of matrix multiplication. It's not very complicated, but it's something that's not that visible in standard linear algebra because we're usually working there in a fixed framework. We're working with 3 by 3 matrices or 4 by 5 matrices or something like that. So we have a fixed kind of framework. It doesn't really make sense to shift everything down because then we would sort of move out of the domain in which we're working. But now we have this more flexible, bigger point of view. We're working in the entire plane. We're not restricted by any kind of boundaries. And so the shifting is a more natural thing that's more visible to us. Here's a little exercise. You can verify the theorem for these 2 particular maxels. So they're kind of little maxels, only 2 by 2. Here's 2, 1, 3, 4, that maxel there, and the n is 5, 2, 1, 3. And you can try, say, for different values of k and just verify that the theorem works. And even better, you can sort of write out proofs of why these formulas hold. So we're now in quite a nice position. We've extended our labeling or our index sets. So now we can consider indices that take on arbitrary integer values. This is a big expansion. But we also want to expand in another important way, okay, which is different but still utilizes this bigger picture of having integers at our disposal now, not just natural numbers. And that is that we want to extend things so that the actual entries of our maxels are themselves possibly negative. Right? We don't always want to be just considering natural number entries. We want to have a -2 possibly in a matrix. Of course we want to do that. So we have to set that up though, because this 2 here represents a multiplicity of a certain number of pixels. So in order to make sense of what that might mean if that was minus 2 instead, we have to get our heads around what does it mean to talk about minus 2 pixels? Or in fact, what does it mean to talk about minus 2 anythings? So we've talked about minus 2. We've introduced minus 2 as this abstract integer object, something that we write down. But how do we multiply that minus 2 times something else? In particular, how do we multiply minus 2 times a pixel? To understand that, we are going to have to go back to our particle-antiparticle orientation coming from physics and really extend that now. So it's a consequence of having our negative numbers set up the way we have them, that we are going to have to consider this particle-antiparticle duality in a much wider context. That's going to further challenge our intuitions and the familiar ways of thinking that we're used to. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.